The rest of it's due tomorrow. Okay, and I gave you the option to go ahead and starting some other of it last night if you needed to. Test is tomorrow. All right, so the practice problem number 19 states if 15.50 grams of propane, which is a gas, it states, is reacted with 25 grams of oxygen. You want to find all these things: limiting reactant, theoretical yield of carbon dioxide, and a percent yield of 12 grams of carbon dioxide is collected. So the first thing, well, it's not the first thing you have to do, but what I always like to start with is a balanced equation. You're going to have a balanced equation any way you go about it. So I prefer to do the balanced equation first. One of the things you're going to have is a balanced equation. So we have propane. Now, if you didn't remember or be able to figure out in your head a simple molecular formula for propane, what you should remember from Unit 4 is how to write a condensed structural formula for propane. Propane, the PROP prefix, means you have three carbon groupings, three hydrogen carbon groupings. And when you write that in a condensed structural formula, it comes out looking like this: CH3, CH2, CH3. Okay? And the A and E suffix on this means there's nothing but single bonds. So that's why you get the three hydrogens here and two here and three here. All right, so then to write a simpler molecular formula to make all the work a little easier, I guess, I think it is anyway. I'm just going to condense all this down then to, I'm going to say three carbons, so I'm going to say C3, and then count the hydrogens, and I got H8. Okay? And you could leave it like this. It's perfectly okay to write your equations with this formula. Nothing wrong with that. I just prefer to do it this way. Okay? I won't count it wrong if you do it this way. All right? In either case, this is going to be a gas. Let's see, and then we're going to react that with oxygen. And you are supposed to know that oxygen is always going to be O2 for us. Okay? Oxygen in the air is O2. And anytime you're reacting a hydrocarbon with oxygen, you're supposed to know from Unit 5 you always get the same products: CO2 and H2O. And since this is a combustion reaction, we always list this water, the physical state of water, as being a gas, because there's a lot of heat when you have combustion. Okay? So that's the unbalanced equation. I've got basically a skeletal arrangement here of the equation now.
What does that say, C3H?
C3H8. I just counted the number of carbons and counted the number of hydrogens and made us over a little bit simpler molecular formula here. Okay? Now I want to balance the overall equation. So I'm going to list all the elements I have: carbon, hydrogen, and oxygen. Make a simple grid. I want to do an atom inventory and balance the equation. I'm starting out with 3 carbons, 8 hydrogens, and 2 oxygens on the left, 1 carbon. I've got 2 oxygens here and 1 here. So right now on the right hand side I've got 3 oxygens and I've got 2 hydrogens. I want to use only coefficients in front of each of these chemical formulas. I can't mess with the formulas once they're done. I can only use coefficients in the balanced equation to get all the atoms to be equal on both sides. So what I'm going to do is use coefficients here. I'm going to start with a 3 here. Remember, you always balance oxygen last and hydrogen next to last. So we have to start with carbon here. That gives me 3 carbons, and it changes the number of oxygens. So now, instead of just 2 oxygens, I have 2 times 3, or 6 oxygens, and then the 1 here. So at the moment, I have 7 oxygens. Okay? So I'm going to save oxygen for last. I'm going to balance hydrogen now. To get hydrogen balance, since I have 8 on the left and 2 on the right, I'm going to put a 4 here. That'll change the number of hydrogens to 4. 4 times 2 is 8. I'm sorry, change the number of hydrogens to 8. 4 times 2 is 8. But it also changes the number of oxygens on us. So So let's go back and recount everything. I got 3 times 2, or 6 oxygens there, plus the 4 here. So I've got 10 oxygens on the right-hand side. Oh, okay, wasn't plugged in tight. And then to get 10 oxygens on the left, I'll put a 5 here, and 5 times 2 gives me 10 oxygens, and the equation is balanced. So that has to be done in order to do stoichiometry. Stoichiometry is any time you go from one chemical species to another. You've got to do stoichiometry. So now that we've done this, we're ready to figure out which one of these two reactants is the limiting reactant. By definition, the limiting reactant is the chemical that runs out first in a chemical reaction, and therefore the reaction has to stop when that chemical runs out. So we're going to try to figure out which one is the limiting reactant. We can either start with this chemical, or we can start with this chemical. It doesn't matter which one. I'm going to start with this one, but again, it doesn't really matter that I start with this one. I have to start doing the stoichiometry with the given amount, the 15.50 grams of propane. Okay, and that's going to go over 1. Always your starting amounts go over 1. So 15.50 grams C3H8 goes over the number 1. Wait. You okay now?
Yeah.
Okay. And I need to first do a molar mass conversion to convert grams of this stuff into moles. So I have to have a molar mass calculation to do that. I like to do my molar mass calculations kind of along the bottom just to give me room to do all my stoichiometry up here. You don't have to do it that way. It's not required. All right, but I've got 1 carbon here in the formula. Now remember, molar mass, we only count the number of atoms in the formula. We're not going to worry about these coefficients in the equation when we're doing molar mass calculations. Only the number of atoms in the formula. That's the subscripts here. And so we've got carbon, and you look up the atomic mass on the periodic table, the average atomic mass, and that's for carbon, that's 12.0107. I have 3 of those in the formula. And hydrogen's atomic mass on the periodic table, average atomic mass, is 1.00794, and I've got 8 of those in the formula. Okay. The definition of molar mass is the sum of all the atomic masses of all the atoms in a formula, and we're just using a system here where we can multiply hydrogen by 8 to get a sum rather than try to add this number 3 times and this number 8 times. You could do that. That'd be perfectly okay to do that. This just makes it a little bit faster when you have more complex formulas like this. So 12.0107 times 3, it's going to give us 36.0321. And then hydrogen's 1.00794 times 8. And I will keep all my numbers lined up nice and neat here. 8.06352. I want to keep it lined up nice and neat because then I can see that I've got an empty slot in this column, and that'll tell me what to round off after I add. So I add these two numbers together now. And I get 44.09562. But that last digit under the arrow in that column gets rounded off. And then we're going to show an arrow to indicate that we're rounding off. And we have 44.0956. And the definition of molar mass is the sum of all the atomic masses of all the atoms in the formula written in grams. But in this class, you also have to go one more step beyond that and say that's grams of C3H8, and say that's equal to 1 mole of C3H8. And this 1 mole is always going to be 1 mole here. You're never going to look up here and say, well, that's 5 something or 3 something from the coefficients. That has nothing to do with what this is. This mass is always equal to 1 mole. And the reason we do that is I want you to understand and reinforce this for yourself over and over again, that The conversion units always have to have an equality statement. Even if you don't write an equality statement, there is an equality statement. Okay, we're going to write them to make that point over and over, and if you write it every time, you tend to make less mistakes up here. So it's actually a tool to help you be more successful in getting correct answers. What I want to do now is to match these units and species here in the starting amount on the bottom with this fraction. And in the equality statement down here, the side of the equality statement with the matching units and species is this side right here. And so I want to put that on the bottom, 44.0956 grams C3H8. And then I'm going to put 1 mole C3H8. The other side of the equality statement down here at the bottom goes on the top. All right, now we can cancel units, just like we cancel x's and y's in algebra, and the species can be canceled in the same way. Now that we have moles of C3H8, we're ready to do a molar ratio to go from one species to another. To convert from one measurement unit to another, you need a conversion unit. Conversion units always need equality statements. To go from one species to another, you need a molar ratio. Molar ratios come from the balanced equation. So these coefficients in the equation can be thought of as being individual molecules or formula units. So I'd have 1 formula unit of propane here and 5 formula units of oxygen. But you can also use that to mean moles of that formula unit in this formula unit. 5 moles of this one, 1 mole of this one, because a mole is a counting number. It's equal to 6.02 times 10 to the 23rd particles. So I can take 1 mole then of C3H8. Again, I'm matching the units and species on the top here and the bottom here. And since I'm going from one reactant species to another, I need to find out which one of these is the limiting reactant. I want to put on the top of this the other reactant, because I'm trying to get to the other reactant at this point. So that's 5 moles C3H8. I'm going to cancel the units, cancel the species. I'm sorry, that shouldn't be C3H8. That should be O2, shouldn't it? Why don't you speak up and tell me that? Okay. All right. So I want O2 on the top here. Okay. Now that we've got O2 here, I'm ready to convert that to grams. Okay. So I need another molar mass for oxygen here. Oxygen's atomic mass on the periodic table, and you'll have that test reference for your test. You have a copy of it already. The oxygen's atomic mass, or average atomic mass, is 15.9994. We're going to multiply it by 2 because the molar mass is always the sum of all the atomic masses of all the atoms in a formula times 2. And we multiply 15.994 times 2. We get 31.9988. Okay, and again, that's going to be, I don't have to round anything off here. There's no addition over here to round anything off. We're going to put grams of O2 is equal to 1 mole of O2. There's the equality statement we need for this conversion unit right here. And we're going to put the 1 mole on the bottom because, again, we want to match the units and species that I have here on the bottom here. So this side of the equality statement goes here, O2. And then on the top we'll have the other side of the equality statement here, this molar mass equality statement, 31.9988 grams of O2. Cancel the units of moles, cancel the species oxygen, and we're ready to do the math. Okay? Okay, I'm going to stop that for a second.